Hey everybody. Um, Today we're going to start on chapter 2 of the book by Neiman, and we're going to take some elements of quantum mechanics, some principles that we need to know in order to use some tools in quantum mechanics for understanding devices. So the first principle is energy quanta. And specifically here we mean photons, which are the quanta of electromagnetic energy. So light particles. And I don't mean the opposite of heavy, I mean electromagnetic waves. So there were two experiments that showed that this was a real concept that needed to be accepted. So the first one is the photoelectric effect. So this is done by shining light of different wavelengths onto a metal held in a vacuum. And then if you put a remote electrode out here and ground this one and put a bias on this one, oops, battery not a capacitor, you'll collect a current, carried through the vacuum by the ejected electrons. But the thing is that the wavelength of the light matters, not the intensity of the light. So the current that's carried through the vacuum is going to be proportional to the intensity of certain wavelengths of light, but there's a thresholding effect where basically you get, so here's the current again, and plotted versus the wavelength of light. And so you get some current until you hit a threshold where the light, which is towards the red end of the spectrum, does not actually have enough energy to pull the electrons out of the metal. And what you're really fighting against is sort of I'll draw an analogy here. You have an electron C inside the metal, and the electrons have to be given enough energy, so here's our energy axis, to make it out of the metal here. And that amount of energy is called the work function. So there's some sort of binding energy that keeps the electrons inside the metal, which needs to be overcome by the light when it comes in order to eject an electron. So let's go to the next page. So the second experiment was blackbody radiation. And the book doesn't talk as much about this, but I'll give you a brief outline, which is the idea that if you had a cavity, sometimes they refer to this blackbody radiation as cavity radiation, and you want to figure out the electromagnetic energy which is in thermal equilibrium at a given temperature, you would sort of imagine this cavity which is made entirely of mirrors, and then ask yourself which electromagnetic modes could exist inside there, and then how much energy would be in each mode. And because because you have a wave which has to be a standing wave if it's to exist inside this cavity, you have a discrete set of wavelengths which are allowed. So we could index those modes by lambda sub n, and we could go on and calculate how much energy density would be inside that cavity. And when this was done by Planck, the idea of quanta emerged, because the total energy density inside this box would diverge unless you assumed that the energy of these waves scaled inversely with the wavelength. So energy has to be proportional to 1 over wavelength. So that brings us to our second principle, of wave-particle duality. So given these observations, de Broglie came up with the idea that the momentum of a particle would be inversely proportional to its wavelength. And P here is the symbol for momentum. H is Planck's constant. And of course wavelength is the distance between troughs or peaks on a wave. So this was very important finding, because it connected back to the previous finding from the black-body law, because the kinetic energy can be expressed as p squared over 2m equals the kinetic energy for electrons and other massive particles, and P times C is the energy of photons. So in both cases, you can use the momentum to determine energy, or vice versa. And therefore, you could figure out that if we go back also to the photoelectric effect, the fact that there's this cutoff wavelength here tells you that the photon energy had to be higher than the work function in order to eject electrons. So there's two sides of this wave-particle duality. So first, EM waves, in some cases, especially when they're interacting with electrons, should be considered as photons, or discrete packets of electromagnetic energy. And on the other hand, electrons could exhibit some wave-like phenomena, such as interference and diffraction. And the electron diffraction was first observed by Davison and Germer by sending an accelerated beam of electrons into a very polished piece of nickel, And what they saw is that the electrons didn't just bounce off in the backscatter direction, but instead they went out in very specific directions that were diffracted beams. So by that time, they knew that nickel was a crystal, and so the atoms were arranged sort of like a diffraction grating in regular rows with fixed spacing between them. And they had observed this by X-ray diffraction, and so the appearance of these discrete beams going out in fixed directions told them that diffraction was also happening from the electrons. We'll also use this idea of interference, specifically when we do the analogous problem. We talked about the black body problem where you had mirrored cavities. So the analogous problem for electrons would be a potential well, which means that the potential energy is given some value outside, which is higher than the value inside this well. So the simplest example is where the potential energy is infinite on both sides, but zero in the middle. And in this case, if we consider an electron to be a wave, well, we see that it has to interfere with itself, and that standing waves will appear, or stationary states in the quantum mechanics parlance, and that this, this electron wave has to interfere with itself and form a certain interference pattern, and that determines the allowed modes in this structure. So the same problem could be solved also in a electromagnetic waveguide. So, for example, if you have a slab waveguide like this, that it's just a stack of materials such as air and glass, let's say, so n greater than 1 in the middle, the allowed mode structures are similar. You have to have an integer number of half wavelengths fitting inside the thickness of the waveguide region. And I guess I should label this axis here as x going from 0 to a. Okay, and the last sort of ingredient for our quantum mechanics is uncertainty. And what this means is that the uncertainty in position and the uncertainty in momentum, or the uncertainty in energy and time, have to be greater than a certain number. And it turns out that this is usually stated as h bar over 2. So it means that you can't know the position exactly at the same time as momentum, or you can't know when something occurred exactly, as well as knowing exactly what its energy was. And we'll use this to understand some of the features of quantum states inside semiconductors. So, for example, a plane wave has a formula that looks like a times cosine omega t minus kx. So this is a traveling wave traveling to the right. So I could draw its crusts and troughs like this, and if you took a picture of it at a certain spot, as time evolved, it would move to the right. And the thing about a cosine wave is it goes on forever. So in a sense, delta x is infinity, and that means that we know its momentum exactly. So delta p can be 0. And this is exactly what we see. This k here can be defined as 2 pi over lambda. And so what we could say is that this particular plane wave is a function for which we know the momentum exactly. And another way to say that is that it's a momentum eigenstate. So this k here tells you the inverse of the wavelength, and we can actually generalize it to be a vector, and that'll tell you in which direction it's traveling. Okay, so those are the three basic principles that we need to use throughout this chapter on quantum mechanics, as well as throughout the rest of the course. So the next topic to come up is Schrödinger's wave equation, and we'll move on to that